Hi everyone, it's Mrs. Griffin with the Unit 4 Lesson 5 continued video. We're going to start off at number 11, and we're going to talk about a new idea of supplements of congruent angles are congruent. So what that means is if I have two pairs of supplements, and I happen to know that one from each pair is the same, then that means that the other pair has to be the same too. And the same applies with complements, but this particular problem focuses on supplements. So if we look at our givens, we are told that ABE bisects angle CAD. So CAD is over here, and therefore it gets split into two congruent parts, angle 1 and angle 2, because an angle bisector divides an angle into two congruent angles. And that is an angle pair for our triangles because I have one in each triangle. And then we also have this other given that angle CBE, which is out here, it's angle 5, is congruent to angle DBE, which is out here, it's angle 6. I'm actually going to put those in parentheses right here and rename them because that's easier to write. Now that's not an angle pair for these triangles because those are outside of the triangles. So I can't use those as an angle pair like I could with 1 and 2. But what I can do is notice that there is some supplements going on here because these are linear pairs. So angle 3 and 5 make a linear pair. That means they're supplements to one another. So I can write that angle 3 is a supplement of angle 5. And in the same way, I can write that angle 4 is a supplement of angle 6. And I know this because linear pairs are supplements. And that came from the picture. I don't have to write a P in a table proof though. Because I know that 5 and 6 were congruent from the given, that means that 3 and 4 also have to be congruent because supplements of congruent angles are congruent. And that's how I can put into my proof that angle 3 is congruent to angle 4. And now I have an angle pair in the triangle, so I can use those to prove the triangles are congruent. I also have reflexive because those triangles are sharing side AB. So AB is congruent to AB. And now I have enough to show that my triangles are congruent by angle side angle. So triangle CAB is congruent to triangle DAB. And finally, AC would be congruent to AD using CPCTC because those are sides of these two triangles that I just proved were congruent. All right, we're going to skip number 12. And I'm also going to focus on another kind of strange theorem that treats our midpoints and bisectors a little differently than we're used to seeing them. So if we look at number 13, we have a diagram, we have a triangle, and they're telling us that in this triangle, MH is congruent to AH. Okay, and they're telling us that AB and MT are medians. So that means AB and MT both go from a vertex to a midpoint. So I'm going to do the median idea first. A median connects a vertex to the opposite midpoint. So AB connects vertex A to the opposite midpoint B, which means that B is a midpoint of MH. And for MT, it goes from vertex M, therefore, to midpoint T. And so T has to be a midpoint of AH. And then because we know that a midpoint is going to divide a segment to two congruent segments, we normally would start talking about the pieces. Now don't do what I'm doing in red because I want to show you something. If we said that B was going to then divide MH into two congruent pieces, we would have MB is congruent to BH If we tried to do the same thing with t, I have to use a different number of arc marks because I don't know those two little pieces are congruent to the big ones unless I address this in the way that I have up here in these proof blocks. And so here's how we're going to do this. Instead of using our midpoint to talk about individual pieces, I'm going to use them to talk about halves. All right. Another reason that I know I need to do that is because I am trying to deal with triangle MBA and triangle MTA, and those aren't even going to use BH and TH. I don't even need those in my proof. So since I'm focusing in on those triangles, I'm going to talk about the parts of those sides that end up the same. Here's how we're going to do it. We're going to say a midpoint cuts a segment in half. That way I can talk about just MB and how it's half of MH. And then I'm going to do the same thing with TA from the pink triangle. I'm going to say that TA is half of AH. That way, when I go to mark them off, since I know that MH and AH are congruent from my given up here, I'll be able to say that I'm going to use the same number of tick marks on AT. The reason that I'll put in my reason column is that halves of congruent segments are congruent. So since MB and TA are half of segments that are the same length, they have to be the same length too. They're half of the same thing, so they're equal. And then finally, we need to finish our triangle proof up. So now that I have MB and TA, I'm noticing I have reflexive MA, congruent to itself. And there's another side pair, or a side pair. And then I have to find something more. And here's the trick. Go back to the fact that MH is congruent to AH. That makes this an isosceles triangle. And we have those angles down there that would be congruent to one another. And this one happens to be in the pink triangle, and this one happens to be in the yellow triangle. Separated, you can see that angle A is here, TMA, and angle M is here, angle BMA. So now that I have that, I'm going to add it into my proof. So angle BMA, with all the lines there, I'm going to use all three letters. It's too hard to label with numbers then. It's congruent to TAM, because isosceles triangles have two congruent sides. Across from two congruent base angles. And there's an angle pair. And now I have enough to show that my triangles are congruent by side, angle, side. I'm running out of room. Triangle MBA is congruent to triangle ATM. And then I could get my angles. Angle MBA congruent to angle ATM by CPCTC. All right. And then this last one's going to have a very similar concept, but from bisect instead of from midpoint. So we have a parallelogram. Because we have a parallelogram, we know a lot of different things about it. So I'm going to focus in on the fact that I need angle ADF, which is clearly in this yellow triangle, to be congruent to angle CBE, which is clearly in this pink triangle. I'm going to focus in on what I can do from that. So if I'm thinking about my parallelogram, I know opposite sides of a parallelogram are congruent. And so I could say AF is congruent to CE, and that gets me a side pair from these triangles. I also now have from my givens that, from my parallelogram, that opposite angles are congruent. And that can give me that angle F is congruent to angle E. Now in my givens I have bisectors. Normally, we would talk about the different halves, but just like before, we don't want this to be congruent to that and this to be congruent to that, because that won't give you the same number of tick marks for the triangles. They wouldn't be the right corresponding pieces. They don't go together that way. So instead, we're going to talk about how they're halves of congruent things. So we know that FD has to be half of FC, and BE, the pink one, has to be half of AE, because a segment bisector cuts a segment in half. Now, if they were half of the same thing, they would be congruent. I don't currently have anything that says that FC and AE are the same. But if you look at what they are, FC and AE are the same because they're also opposite sides of the parallelogram. So I can include them in step 2. AE congruent to FC. And since they are equal, that means that FD from here has to be congruent to BE from here because they're half of the same amount. So halves of congruent segments are congruent, just like we used in the previous example. And that's how I would know that BE was congruent to FD, and that would be how I would get my side angle side to prove that the yellow triangle AFD is congruent to the pink triangle CEB. And then finally, I can use CPC-TC to say that angle ADF is congruent to angle CBE. All right, see you in class.